Could wormholes be real shortcuts through space and time? This question has fascinated scientists and science fiction fans alike for decades. The concept of wormholes suggests a tunnel-like structure connecting two distant points in space. Imagine traveling from one side of the universe to the other in an instant. Wormholes challenge our understanding of physics and the universe. Are these cosmic shortcuts purely theoretical, or could they exist somewhere out there, waiting to be discovered? A wormhole, in simple terms, is a hypothetical tunnel that connects two separate points in space and time. Think of it as a bridge, or shortcut through the fabric of the universe. If space were a piece of paper, a wormhole would be like folding the paper and poking a hole through it, creating a direct path between two distant locations. This visual analogy helps us grasp the idea of a wormhole. Wormholes are solutions to equations in Einstein's theory of general relativity. They suggest that space and time can be curved and twisted in such a way that two distant points become connected by a short path. However, this idea remains purely theoretical, with no experimental evidence to support it. Understanding wormholes requires us to think beyond our everyday experiences. In 1935, physicists Albert Einstein and Nathan Rosen introduced the concept of wormholes as a solution to the equations of general relativity. Their work described what they called Einstein-Rosen bridges, theoretical constructs connecting two separate points in spacetime. Einstein's theory of general relativity revolutionized our understanding of gravity, describing it as a curvature of space and time caused by massive objects. According to this theory, massive objects like stars and planets warp the fabric of spacetime around them. Einstein and Rosen's work suggested that this curvature could be so extreme that it creates a tunnel-like structure, a wormhole. However, it was not initially clear whether these structures could exist in reality. Einstein and Rosen's bridges were found to be unstable, collapsing too quickly for anything to pass through them. This led to further exploration and refinement of the concept over the decades. The theoretical foundation laid by Einstein and Rosen opened the door to new possibilities in physics and cosmology. Wormholes can be classified into two main types: traversable and non-traversable. Traversable wormholes are those that, in theory, could allow matter to pass through them and emerge on the other side. Non-traversable wormholes, on the other hand, cannot be used for travel because they collapse too quickly or have other prohibitive characteristics. Traversable wormholes are the ones that capture our imagination, suggesting the possibility of interstellar travel. However, creating and maintaining a traversable wormhole requires conditions that are far beyond our current technological capabilities. Non-traversable wormholes exist purely as mathematical solutions to the equations of general relativity. These wormholes might connect different regions of spacetime, but they collapse too quickly for anything to travel through them. Understanding the distinction between these two types of wormholes helps us grasp the challenges and possibilities they present. Wormholes in science fiction, portals to new worlds and dimensions. Science fiction has long been fascinated with the idea of wormholes. These mysterious tunnels through space and time have been depicted as portals to new worlds, alternate dimensions, and even different times. One of the most famous portrayals of wormholes in science fiction is in the movie Interstellar, where astronauts travel through a wormhole near Saturn to reach a distant galaxy. Another iconic example is the TV series Stargate, where a network of wormholes connects different planets across the universe. Science fiction often takes liberties with scientific accuracy to create compelling stories. Wormholes are portrayed as stable and easily navigable, which is far from the current scientific understanding. However, these fictional depictions inspire curiosity and wonder, encouraging people to learn more about the real science behind wormholes. The scientific challenges: creating and stabilizing wormholes. Creating and stabilizing a wormhole presents enormous scientific challenges. Theoretical physics suggests that wormholes could exist, but turning this idea into reality is a different story. One of the main challenges is the need for exotic matter to keep a wormhole open. Exotic matter, with its negative energy density, is required to counteract the natural tendency of a wormhole to collapse. Without exotic matter, any wormhole that forms would collapse almost instantly, preventing any travel through it. Another challenge is the immense amount of energy required to create a wormhole, far beyond our current technological capabilities. These scientific challenges highlight the gap between theory and practice. Exotic matter and energy requirements. The key to wormholes? Exotic matter is the key to creating and stabilizing wormholes. This hypothetical substance has properties that are vastly different from any known matter. It would have negative energy density, which is crucial for counteracting the gravitational forces that would cause a wormhole to collapse. The concept of exotic matter arises from the equations of general relativity. However, exotic matter has never been theoretical. The energy requirements for creating a wormhole are also staggering, far beyond what we can currently generate. Researchers are exploring various approaches to understand and possibly harness exotic matter. Advances in this area could potentially unlock the secrets of wormholes and other exotic phenomena. Wormholes and time travel. Paradoxes and possibilities. Wormholes are not just portals through space, they could also theoretically allow for travel through time. This idea stems from the fact that wormholes connect different points in space-time. If one end of a wormhole is in a different time than the other, traveling through it could result in moving to a different time. The concept of time travel through wormholes raises intriguing possibilities and paradoxes, such as the famous grandfather paradox. Physicists have explored various models to address these paradoxes, including mechanisms like parallel universes or closed time-like curves. While the idea of time travel through wormholes is fascinating, it remains highly theoretical. The scientific challenges in creating and stabilizing wormholes, combined with the complexities of time travel, make it a topic of speculation rather than practical reality. Current research, quantum physics, and general relativity on wormholes. Current research on wormholes is at the intersection of quantum physics and general relativity. These two pillars of modern physics offer different perspectives on the nature of the universe and the possibility of wormholes. Bridging the gap between them is one of the great challenges in theoretical physics. Quantum physics deals with the behavior of particles at the smallest scales, introducing concepts like quantum entanglement and the uncertainty principle. General relativity describes the large-scale structure of the universe, explaining how massive objects curve space-time. Researchers are exploring various approaches to unify these two theories, with quantum gravity being a promising avenue. Advances in this field could provide new insights into the nature of wormholes and other exotic phenomena. The role of exotic matter. Can we harness it? Exotic matter is the theoretical substance that could make wormholes possible. Its unique properties, such as negative energy density, are essential for keeping a wormhole open. But can we harness exotic matter, or is it merely a figment of theoretical physics? Some theories suggest that exotic matter could arise in certain high-energy conditions, such as those found in particle accelerators or near black holes. However, creating and manipulating exotic matter in a controlled laboratory setting remains a significant challenge. One approach to studying exotic matter is through the concept of the Casimir effect, where negative energy can be observed between two closely spaced plates. Harnessing exotic matter would require breakthroughs in our understanding of quantum field theory and advanced technological capabilities. While we are still far from harnessing exotic matter for practical use, the journey itself is a source of inspiration and discovery. Future advancements. What might the next decades bring? The future of wormhole research is filled with potential advancements and discoveries. As our understanding of quantum physics and general relativity deepens, we may uncover new insights into the nature of wormholes and the possibilities they present. The next few decades could bring significant breakthroughs in this intriguing field. One area of focus is the development of new technologies that could probe the properties of space-time at unprecedented scales. Advanced particle accelerators, space telescopes, and quantum computers could provide new data and theoretical models to test the existence and stability of wormholes. Another promising direction is the exploration of quantum gravity, which seeks to unify general relativity and quantum mechanics. Collaboration is crucial in advancing our understanding of wormholes. The future holds exciting possibilities for wormhole research. The reality of wormholes. Fact or fiction? Are wormholes fact or fiction? This question lies at the heart of our exploration. While wormholes are fascinating from a theoretical perspective, Their existence and practicality remain uncertain. The scientific challenges in creating and stabilizing wormholes are immense, and we have yet to observe any direct evidence of their existence. Wormholes are solutions to the equations of general relativity, but they require exotic matter and immense energy to remain stable. These requirements push the boundaries of our current technological and scientific capabilities. Science fiction has popularized the idea of wormholes, presenting them as portals to new worlds and dimensions. While fiction can spark interest and imagination, it is essential to distinguish between imaginative storytelling and scientific reality. The pursuit of wormholes is a testament to human curiosity and the drive to explore the unknown. Conclusion: inspiring scientific curiosity through wormholes. In conclusion, wormholes represent one of the most intriguing concepts in modern physics. They challenge our understanding of space, time, and reality, blending science with the boundless creativity of science fiction. While the existence and practicality of wormholes remain uncertain, they continue to inspire scientific curiosity and exploration. The journey to understand wormholes involves cutting-edge research in quantum physics, general relativity, and advanced technology. Whether they remain a theoretical concept or become a reality, wormholes will continue to inspire scientists and storytellers alike. Stay curious and keep exploring the wonders of the universe.